Folks, we are now ready for section 4.4, additional equations and inequalities. And I'll just warn you, there's a whole bunch of different types in here, so we're just going to take them one by one. The first type that we're going to look at is called a radical equation. And a radical equation contains radicals of some root. It could be a squared root, a cubed root, etc. So for example, in number 1, we have the cubed root of the quantity x minus 2 equals 4. The radical is isolated, and so we need to get rid of that radical. Well, radicals like square roots and cubed roots have an inverse operation. Just like addition and subtraction are inverse operations, multiplication and division are inverse operations, radicals and powers, exponents, are inverse operations. So if you've got a cubed root, how to get rid of that is we're going to take the cube of both sides. And what that does is basically that cubed and that cubed root undo each other. I'll show you in a minute how it works with fraction exponents, but that leaves us with just the radicand on the inside. And then we have 4 cubed, which is 64. We can then add 2 to both sides and we get x equals 66. In number 2, it can be a little bit more difficult because we have 2 radicals, one on each side. So if we start with a square root of x minus 10 equals a negative square root of x minus 20, what we can do is still square both sides. But remember, when you're squaring 2 terms like that, you have to square both of them together, not separately. And then we can square the right-hand side. And notice if we square a negative, negative times a negative gives us a positive. And then this is an understood square root. And so we're left with just the radicand on the right, x minus 20. But on the left, we would need to expand it. And that would give us an x minus 20 square root of x plus 100. Now you may be wondering how we got that. So if you don't remember your binomial squares, then you can expand it. And when you distribute, we get the square root of x squared minus 10 square root of x minus 10 square root of x. Negative 10 times 10 gives us a positive 100. So if you square a square root, you're left with just the radicand underneath. We combined like radicals, just like we do like terms, negative 20 square root of x and then plus 100. So that's how we got the left-hand side. So now that we've gotten rid of the big square root, like we did, we need to turn around and isolate the other square root and get it by itself. So we can subtract x from both sides. And we can also subtract 100 from both sides. We can do that in the same step. That will leave us with a negative 20 square root of x equals a negative 120. So notice not only do these 2 x's add to 0 and these 2 hundreds add up to 0, these 2 x's would also, or I should say subtract to 0. We still need to get rid of that negative 20. So when we divide both sides by negative 20, we would be left with the square root of x equals a positive 6. And now we get rid of that square root by squaring both sides. And we get x equals 36. So I know it seems almost like doing it in reverse, but we've actually seen square roots before, but you may not be that familiar with rational powers. If you have a rational power like this, it's actually representing some radical. If you have the nth radical, and again, this n is what we call the index. So that tells us if it's a square root or cubed root or fourth root. That r is the exponent of your radicand, or what's underneath that radical. And we can write it as a fractional exponent where we keep the base and we keep that exponent r. We just write that n underneath. And I know it looks kind of weird when that fraction is written kind of sideways like that, but I want you to be sure to note that that fraction is in fact in the exponent position. That's another reason why if we had, say, the cubed root of x and we were to cube it, that means we would have x cubed and that cube would be divided by 3, and we would get x to the first. In other words, the radicand underneath. So in example 3, we have the quantity x minus 5 taken to the exponent of 3/2 plus 8 equals 72. So just like with radicals, you want to isolate them in order to get rid of them. We're going to do the same thing here. We subtract 8 from both sides. That's going to leave us with the quantity x minus 5 to the 3/2 equals 64. So there's a couple of different ways we can do this. Just like with the radicals, we would undo that radical, or we would take that inverse operation by either squaring it or cubing it, depending on what kind of radical we have. You can do this in 1 step, or you can do it in 2. If we do it in 2 steps, we would focus on this denominator of that exponent. So we would take both sides to that power, whatever power that is. So in this case, since it's to the power of 3/2 and 2 is in the denominator, we're going to square both sides. Remember our exponent operations. If you have a power to a power, you multiply. So that means these two reduce. So that would leave us with x minus 5 cubed equals 4,096. That's 64 squared. Now we've got a cube, so we want to cube root it. So we can take the cube root of the left and the cube root of the right. And since it's a cube, we don't have to worry about a positive and a negative. The sign is going to be whatever it is. So that leaves us with an x minus 5 on the left and a 16 on the right. Now, you may be wondering how we get the 16. Your calculator may have a cubed root. If not, you can put it in your calculator as 4,096 to the power of, and be sure you put this fraction in parentheses, to the power of 1/3. You can write it as that fractional exponent, and that will give you the 16. So either, if your calculator is a cubed root, go ahead and put in the cubed root. Otherwise, even if you have a scientific calculator, you could put it in this way. So now we still want to get our x by itself. So when we add 5 to both sides, we would end up with x equals 21. Now let's take a look at different equations in quadratic form. So an equation is said to be in quadratic form if the leading variable is the square of the middle variable. So in other words, if we have a to something here plus b to something here plus c, whatever you have there as your middle, this first guy is going to be the square of whatever that is in the middle, okay? So think of what a generic quadratic equation might look like. This would just be an example. You might have 3x squared minus 8x plus 4. So we can notice that in the middle, our variable is just a single x. We still have that single x in the first term, but that single x is being squared. If we're looking at an equation in quadratic form, one example might be 5x to the, 2/7 minus 8x to the 1/7 plus 9. So if we look at the x variables there, we have an x to the 1/7, but then that leading x is still x to the 1/7, but it's being squared. So it's that middle term of x being taken to the power of 2. So to solve these equations in quadratic form, we can use what we call U substitution or just substitution. In example 4 here, it looks kind of quadratic. So notice we have an x squared here in the middle, and we can write this guy as x squared squared. So that tells us we are in quadratic form. So what we can do, we can say, okay, I don't want to work with it using the x to the 4th and x squared. So we're going to let u be that middle variable, the x squared, which means u squared is going to be that x squared squared, or x to the 4th. So if we rewrote this, that would be u squared minus 11u plus 18 equals 0. Now we have rewritten it as a quadratic. So we can use factoring, quadratic equation, quadratic formula, completing the square, any of those methods that we've learned before. I'm going to look, is there factors of 18, positive 18 that would add to a negative 11? Yes. So this would factor into a u minus 9, u minus 2. You can always multiply it out to double check. And when we solve that, that means we get a u equals 9 and a u equals 2. But you got to remember, we didn't have u's to begin with. So that means we have to plug back in the u equals x squared. So we get x squared equals 9. So when you take the square root of both sides, we would get x equals plus or minus 3. And over here, if x squared equals 2, then x would equal plus or minus the square root of 2. So technically, we have 4 different solutions. We have a negative 3, negative square root of 2, square root of 2, and a positive 3 if we were to write them in numerical order. Now let's take a look at another quadratic form, but you've got fractions as exponents. We are going to let our u be that middle fraction, so x to the 1/5, which means u squared should be x to the 1/5 squared. And when we multiply those exponents, we get x to the 2/5, which is what we have at the very front. So when we substitute that in, this first guy is our u squared minus u minus 6 equals 0. The 6 is negative, which means our signs have to be opposites. Don't forget, one positive, one negative. So that would give us a positive 2 and a negative 3, would add up to a negative 1 and multiply to give us a negative 6. So when we set each of these equal to 0, we would get u equals a negative 2 and u equals a positive 3. But again, we need to plug back in the fact that u equals x to the 1/5. So we get x to the 1/5 equals a negative 2, and x to the 1/5 equals 3. So in order to solve these two, we're going to have to take both sides to the power of 5. So the left side would just give us x to the 5/5, which is x to the 1st, and negative 2 to the 5th is a negative 32. And then do the same on the right-hand side. And again, x to the 1/5 to the power of 5 would give us x to the 1st. And 3 to the 5th, after I put that in my calculator, is 243. So this particular example only gave us 2 possible solutions where x equals a negative 32 and 243. Now I know you're thinking, well, the 1/5, it represents a radical and we got a negative answer. Can we still have that? And the answer is yes, because remember, x to the 1/5 would represent the 5th root of x. And we can take an odd radical of any number, positive or negative, because we can, as we can tell here on the left, we took negative 2 to the 5th power and got a negative number back. If I were to take the 5th root of negative 32, I would get a negative 2 back. It's only the even exponents where we would end up with a positive number. So we can't take a square root or a 4th root of a negative number, but we can take an odd root of any sign. So next, we're actually going to be focusing on inequalities instead of equations. And a lot of them, we can do it algebraically. We can also look at it we can also look at it graphically to see what it represents. Now for a quadratic, since we know how to find the zeros of a quadratic, like the x-intercepts, we can set it equal to 0 or the inequality to 0 and figure out where the function is positive, greater than 0, or negative, less than 0, very nicely by testing intervals on all the sides of the zeros. In example 6, we have 2x squared plus 5x is greater than or equal to 3. So if we set this equal to 0 by subtracting 3 from both sides, we would get 2x squared plus 5x minus 3 is greater than or equal to 0. If we factor the left side, we would get the quantity 2x minus 1 times the quantity x plus 3. And we can solve for both of these zeros by setting 2x minus 1 equal to 0 and x plus 3 equals to 0. So on the left, we add 1 to both sides. We get 2x equals 1 and divide both sides by 2. We get a 1/2. And on the right-hand side, we'd subtract 3 from both sides and just get x equals -3. So if we were to focus on this algebraically, we can think of it kind of as the x-axis, where we have x-intercepts at -3 and at a positive 1/2. So we know the graph crosses the x-axis, are exactly at -3 and 1/2. So where would the graph or the function be? We're wanting to know where the function is greater than 0. So in other words, where would those y values be positive? So we can use what we call test points on all sides of these zeros. Okay, so notice those two zeros where they, cross the x-axis, splits up the x-axis into 3 segments. To the left of -3, in between -3 and 1/2, and to the right of 1/2. So let's just choose some x values in those intervals. To the left of x, we could choose -10. In between, I love plugging in 0, makes our life easy. And on the right, choose an easy number, maybe like 1. You could choose 10 or 100. Those are merely choices, but again, it has to be somewhere in those intervals on that number line. So if we were to plug in -10 into the original equation, 2 times -10 squared plus 5 times -10 minus 3, that would give us a 200 minus 50 minus 3. I don't know exactly what that value is, but I definitely know that it's positive, right? We know that the y value, the f of x value, is going to be above the x-axis there. It's positive. If we were to plug in 0, 2 times 0 squared plus 5 times 0 minus 3, well, that gives us a -3. So we know every value in between -3 and 1/2 is going to be negative. If we plug in a 1, you might guess this is going to be positive as well, but we can still check it. Times 1 minus 3, that gives us a 2 plus 5 minus 3, and that's going to end up being a positive number. Looking at where the values give us positives and negatives, and considering that we wanted to know where it was greater than or equal to 0, in other words, positives, this tells us where our intervals are. It's positive here, and it's positive here. So our solutions will be this first interval from -infinity to -3. Oops, it's or equals to, so we're going to use the bracket. And interval from 1/2 to infinity. Another way to consider this is graphically. We know we had zeros at -3 and 1/2. We also know that leading coefficient is positive, which means it opens up. So if these are our x-intercepts, the graph is going to look something like this. Up here, our f of x is greater than 0, and over here, our f of x is greater than 0. In other words, they're positive up here, and it's negative down here in between those two. So the graph can help you determine those values as well. Notice that's the only places they're going to change from positive to negative is at the x-intercepts. So it's helpful if you can find the zeros. You can always use that number line idea. Now, it's not always easy to find those zeros algebraically, especially if you have a power function like this one. In example 7, we have the quantity x plus 5 to the power of 4 less than 16. So instead, we can find the intersection point of both sides and then compare the intervals to see which side is greater or less than the other. So let's first solve for this. Again, it's to the power of 4, so we can take the 4th root of both sides. That would leave us with the radicand of x plus 5 less than, now the 4th root of 16 could be positive or negative 2, okay? Positive or negative 2. Because remember, if we're taking it to the power of 4, that might still work. So we can solve both of these, x plus 5, let's set it equal to find out where it's actually equal to a negative 2, and x plus 5 equal to a positive 2. We subtract 5 from both sides, we get x equals negative 7, and x equals a negative 3. So we can use the number line idea again. We have negative 7 is to the left of negative 3. These are our x values. And since it's strictly less than, we know that these points will not be included because those are the points that would give us 16. Remember, we solved for our x. So the y values at these points are actually equal to 16. So we can split up these intervals again and plug in some points. This time, instead of just knowing where it's positive and negative, because we were comparing to 0, this time they're asking us which x's give us y's smaller than 16. So let's pick a test point to the left of negative 7 on our x's. So maybe, negative 10. So if we had negative 10 plus 5 to the 4th power, that would be negative 5 to the 4th power, which would give us a positive 625y, okay? That y value is definitely larger than 16, okay? So now let's pick another number in between negative 7 and negative 3. Well, since I'm adding it to 5, I might pick an x value of negative 5. So if I plug that into the left, negative 5 plus 5 to the power of 4, that would give me 0 to the 4th power. So that gives me a y value of 0. 0 is definitely less than 16. So I know this interval here would work. We're pretty sure the right hand's not going to work, but we've got to check it anyway. Let's suppose we plug in 0. We like plugging in 0. We get 0 plus 5 to the 4th. And 5 to the 4th gives us also 625 again. So the only interval of x's that gives us values smaller than 16 is the interval between negative 7 and negative 3. Now, we could do this graphing as well. So let's take a look at Desmos for a second. So imagine that we graphed the left side of that inequality and the right side of that inequality as two different equations. So the left-hand side would be y equals the quantity x plus 5 taken to the power of 4. And then the right-hand side would be y equals 16. Now, for y equals 16, notice we're going to have to move this graph down a little bit, or we can zoom out over here and we can notice there is the line where y equals 16. So we have to determine where do they meet and where is it smaller than 16? When is the graph x plus 5 to the power of 4 less than this line, less than 16? And it would be in between these two intersection points. So we can zoom in, make sure that we know what these intersection points are, negative 3 all the way out to negative 7. You can double check it, negative 3 here, all the way out to negative 7, and notice that it's underneath in between those two. So you can also take a look at it graphically as well. Now, I showed you guys one method of solving absolute value equations that also work for inequalities. So that method's not going to change, but I want you guys to understand basically how to determine if we're looking at two intervals or one interval, because that's where a lot of people struggle. So if you recall, that absolute value means the distance from 0. let's say we have this guy over here, and we're saying the distance from 0 is less than a. So the distance is going to be within a units, so a and negative a, it's going to have one interval, okay, between two values where that distance is smaller than a. Likewise, though, if we have a distance from 0 that is larger than a, well, between 0 and a is a units. The distance between 0 and negative a is a units. So if you want a distance larger than that, then it has to be either to the right of a or to the left of a. So we're going to end up with two intervals. Negative infinity, let's say to negative a, union a to infinity. So it really depends, once you get that absolute value by itself, whether you're looking at one interval close to a value, or whether you're looking at two intervals away from a value. In example 8, we have the absolute value of 3x plus 1 is less than or equal to 5. So we're looking at a distance that's small. So this is kind of our hint that we're looking for one interval. So remember, that inside piece could be compared to a positive 5 or a negative 5. So what's inside there could be a positive 1 times the inside, less than or equal to 5. Or it could be the negative version. So we would take negative 1 times the 3x plus 1, less than or equal to 5. So if we distribute a positive 1 on the left, we get 3x plus 1 less than or equal to 5. Subtract 1 from both sides, we get 3x less than or equal to 4. Divide both sides by 3, and we get x is less than or equal to 4/3. We have to distribute that negative 1 to both terms inside that absolute value, not to the 5, okay? Just what's inside that absolute value. So that gives us a negative 3x minus 1 less than or equal to 5. Add 1 to both sides, we get negative 3x less than or equal to 6. But notice here, we have to divide by a negative 3. So that is going to switch our inequality. So that leaves us with an x greater than or equal to a negative 2. Well, remember, we're looking for one interval. If we were to graph both of these intervals on a number line, negative 2 and a positive 4/3, the positive 4/3, the x is less than that number, and it goes all the way this way. But in the second one, the x is greater than or equal to a negative 2, so it goes this way. Remember, we're looking for one interval that could satisfy either one, which means we're looking here where they overlap. So our interval is going to be from negative 2 to a positive 4/3 or 1 1/3. In example 9, we have the absolute value of x minus 8 greater than 7. So this is telling us that we're looking for a distance larger than a number. So it's going to go outwards on the number line. So we're going to have possibly two intervals that we're looking for here. So we're going to do the same two options. Either we have a positive inside, so a positive 1 times the quantity x minus 8 greater than 7, or the inside is going to be the negative version, so negative 1 times the quantity x minus 8 greater than 7. On the first one, if we distribute 1, we get x minus 8 greater than 7. Add 8 to both sides, we get x greater than 15. On the right, we distribute the negative 1 inside the parentheses. We get negative x plus 8 greater than 7. Subtract 8 from both sides, we get a negative 8 greater than a negative 1. Again, I'm going to show the division here. We're going to divide both sides by the negative 1 coefficient of x. But when we do that, we have to switch that inequality, and that will give us a positive x is less than a positive 1. If we were to graph these on a number line, we're looking at 1 and 15. We have x is larger than 15 to the right, and x is smaller than -1 to the left. That gives us two intervals. The first interval on the left goes from -∞ to 1 parentheses. Union, the second interval starts at 15 towards infinity. Notice everything's in parentheses because there's no or equals to sign. So now we have a modeling problem where we have the population P of T of a bacteria culture is given by the function P of T equals a -1500 T squared plus 60,000 T plus 10,000, where T is the time in hours after the culture started. We want to determine the time or times at which the population will be greater than 460,000 organisms. So if we were to write this, we're looking at the function -1500 T squared plus 60,000 T plus 10,000 to be greater than 460,000. Now, again, it didn't say equal to or greater than or at least. We have to be really careful with the wording, whether or not we have that or equals to sign. They want it strictly greater than 460,000 organisms. So we can work this as a quadratic. We can set it equal to, or set the inequality equal to 0. So let's subtract 460,000 from both sides. So if we were to factor out a -1500, that would leave us with a T squared minus 40T plus 300 greater than 0. That trinomial will then factor into T minus 30 times T minus 10. And we would set both of those factors equals to 0. Notice we don't fool with the -15 anymore because there's not a T there to solve for. So we just factored that out to simplify the problem. So we would get two T values, T at 30 and T at 10. So again, if we were to look at those two X values, 10 and 30, we don't want to know where it equals those values, but notice that our original function is opening down, right? Because our leading coefficient is negative. So technically, we know that parabola is going to do this. So we want to know where it's positive or greater than 0 here. Then we're looking between 10 and 30 hours. The culture will have a population greater than 460,000 between 10 and 30 hours. But if you weren't sure about the graphing part to see where it was going to be positive, remember, we can still split it up and use test points. We can use 0 to the left of 10, 20 in between 10 and 30, and maybe 100 to the right of 30. And if we plug it into the equation, once we got it greater than 0, then that would give us a -450,000. Oops, comma's in the wrong place. If we plugged in 20, that would give us a positive value. And if we plugged in 100, that would give us a negative value. So that would still give us positive numbers greater than 0 between 10 and 30. All right. That's it. That is it for this section. If you have any questions, come and see us. That's what we're here for. Bye.